Hi guys, today we're going to start our Unit 5. First lesson is about relations versus functions, function notation, and evaluation. So what is a function? A function is a defined rule or formula that assigns one and only one output, usually f of x, for each input, usually x. So it's like a machine that takes in an input, which is x, to produce an output, f of x. So think about it. This is the defined rule, which is the machine, and we have the x going into that rule or machine and leaves that machine as f of x or an output. So first thing you're going to ask yourself, we have been doing equations in two variables so far. What is the difference between equations in two variables and functions? And the first difference is the notation. When we write an equation in two variables, usually with x and y, but when we write functions with an input and an output, usually x and f of x. To give an example, we have y equals 2x minus 4. That's an equation because we have two variables, x and y. The same equation can be written as a function, f of x equal 2x minus 4, because we have an input, x, and an output, f of x. So basically the difference between these two is how we write the output. For equations we write y, for functions we write f of x. So the second difference between functions and equations in two variables is solutions and outputs. An equation can have no solution, one solution, or many solutions for y. In functions, each input can have one and only one output. Each input is assigned one and only one output. If the input has more than one output, the function is called a relation. It's not a function anymore, it's just a relation. Now let's ask ourselves, what is a relation? A relation is a set of ordered pairs that can be represented by many ways. A relation can be represented by a relation set. This is an example of a relation set where we have points of inputs and outputs. 2, 3, 2, and -1 are the inputs in this relation set. -2 is the output for 2. -4 is the output for 3. -3 is the output of 2. And 1 is the output of -1. So this is a relation because each input has an output. This relation is not a function because -2 has two outputs. And for a relation to be a function, each input in that relation has to have one and only one output. Relations also can be represented by a map diagram. This is a map diagram where we have two groups. The first group is the inputs, and the second group includes the outputs. Since the arrow is going from the left group to the right group, the inputs are in this group, and the outputs are in the second group. So the inputs are 8, 9, 10, and 13, and the outputs are -1, -3, and 5. 8 is an input and it has an output of -1. 9 has an output of -3, 10 has an output of -1, and 13 has an output of 5. Each one of these inputs has one and only one output. That's why this relation represents a function. Relation also can be represented by tables. This is an example of a table where we have the inputs as x values and the outputs as f of x values. If you look at the table, we'll find out that -2 has an input of -16, -1 has an input of -8, 4 has an input of 32, and 48. Since 4 has two outputs, this relation does not represent a function. Relations also can be represented by graphs. This is an example of a relation represented in a graph. Inputs are represented on the x-axis, and outputs are represented on the y-axis, or the f of x values. So if we look at this graph, we'll find out that this graph represents the relations between inputs and outputs. If we take -1 as an example, which is right here, -1 on this graph has an output of 1. So the input for -1 on this graph is 1. Before we move on, guys, I want you to stop the video, finish the class, the first page of the class practice before you move on and watch the second half of the video. So far, we learned that relations can be represented by a relation set, map diagram, and tables, and graphs. We learned that we can look at relation sets, tables, and map diagram to find out if each input has one and only one output to represent a function. Now, we can also look at graphs and find out if they're functions or not by using what we call a vertical line test. A vertical line test is used on graphs to identify if the graph represents a function or not. Let's take a look at our first graph right here. We have a graph. We're trying to figure out if this is a graph of a function or not. We're going to use this line, which is a vertical line, to be able to find out if this a graph represents a function or not. And this is how. All you need to do is to imagine that this line is going through the graph. And if this line crosses the graph in two different places or more, two or more different places, just like what we have here, then this graph is not a function. Let's use another example where we have this graph now, and we're trying to find out if this graph represents a function or not. We're going to use again the vertical line right here, and we're going to imagine that vertical line going through the graph. And if you look here, you'll find out that as the vertical line moves, it crosses the graph in just one spot only. That means that each input on this graph has one and only one output. That's why this graph represents a function. Now, I want you to stop the video again, finish the second page of your classwork before you move on with the video. Now we're going to learn how to evaluate a function. We talked about functions, what they are, how we can represent them, how we can identify them. Now we're going to learn how to evaluate them. this is an example. We have example 1, f of x equals negative 2x plus 3. The question is to find f of negative 3. When I say f of negative 3, I mean that I need to find the output for an input of negative 3. And to find f of negative 3, all I need to do is to switch x with negative 3, because negative 3 is the input, x is the input. By substituting x with a value, it will help me find an output for that input, which is in this case 9. Let's take another example. We need to find f of 2. So again, I'm trying to find the output of an input of 2. That means, again, I'm going to substitute x in the function or the function rule with 2 to try and find out an output in this case, which is basically negative 1. Negative 2 times 2 is negative 4, plus 3 is a negative 1. So on both of these examples, the input is negative 3, the output is 9, the input is 2, and the output is negative 1. Example number 3. Now you are trying to find 3 f of negative 3 plus f of 2. This means that you're trying to find 3 times the output of negative 3 plus the output of 2. And to do that, all I need to do is to substitute f of negative 3 with the output of negative 3, which we got before in example 1, which is 9, and to switch f of 2 with the output of 2, which is in this case the answer we got in example 2, which is negative 1. Now 3 times 9 plus negative 1 is just 26.